You guys feeling good about it? Yes? I'm seeing like blank stares now. Any comments on that? Okay. So I did have a question that came up about how to utilize like the web page. So I changed some of the wording. So it says learning information, I think, now on it. So the learning information is more for you to use as much and as little as you need. So let's see. Okay. So for an example, like on this one, say I am not doing, oh no, this is the old one. So let me go back to lecture 2. So on the learning material, if I am still struggling with any of these topics, this will be like where, so before class, and hopefully as I have this material beforehand, before you even come to class, on the syllabus it says kind of what's the upcoming topic. You also can see like, okay, we covered lecture 3, then lecture 4 is going to be next. Try and review a little bit of the material before you come to class. That way it will go a lot quicker in understanding. So on that, you can go through, and then I have the practice at the beginning. So if you look at the practice problem and you're like, oh, this isn't too bad, I know how to do that, you don't need to go watch the videos, you don't need to read extra, just making sure you're understanding what I've put usually underneath that practice section. So if you're tackling that, you feel comfortable with it, then you really don't need to go on unless you're like, oh, I'm interested in this and I want to learn more. Then feel free to, but know like the other material that's in here is to use as much or little as you need. Same thing, you know, for each section, there's going to be a practice section, there's going to be a reading section, and so on. Okay, does that make more sense how to use the material that's on the website? Okay. All right. So, last time we talked about Ohm's law. Anybody state the expression for Ohm's law, or the equation? Ohm's law is? Awesome. Lots of responses. Great. So memorize that equation or have it very handy to look at a page. Know how to apply it. So understand the polarity. If your current is going the same direction as the plus and the minus, where's your minus on your current? If this is my current, looks kind of like an arrow. Arrow would be this side. So arrow means minus. So minus for the arrow side. So plus on the top, minus on the arrow side. Your voltage, whichever label you have, if it's the same, so on the top it's plus, on the minus, on the bottom it's minus. If they're the same, you will have a positive I times R. If they're going opposite each other, you're going to have a negative I times R. Okay, so that's how you know if it's positive or negative. Power, equation for power. I heard somebody say it. Say it a little louder. You said it right, whoever said it. And it is I times V. I just don't know who said it. But I times V, that is correct. Equivalent resistances, you need to understand series and parallel. And then you can combine resistances to reduce down kind of a network. We're going to go over one more example of that today. And then after that, we're going to move to today's learning objectives, which is voltage dividers, current dividers, potentiometers, and sensors. So looking at how do we now take something from the environment or have something physically change and get a signal out of that that we can then use and use it for some application. Okay. All right, so as I mentioned, you have to understand series and parallel. So how do you know if it's in series or parallel? So these little wires are very confusing to beginning students. So you have to be told what those mean. Does that mean that they are just floating out there, so they're just some dangling little wire? Or are they going to be needed for an extraordinary node and have something put on them? If you're trying to find the equivalence between two locations, say I call it A and B, those are going to be treated as extraordinary. Meaning that there's an element that's going to be there. So these over here on the right would be considered floating. And then A and B are going to be an element on there. So if there is an element, then this means that this node here becomes extraordinary. And this one here becomes extraordinary. Anything floating you can ignore. Okay, so if it's floating, you can just ignore that wire. It's basically like it's not even there. So A and B are going to be series or parallel here?
Parallel.
Okay, good. Parallel. All right, here is my A and B. So I am telling you those two locations are not floating. What is A, B, and C here? Okay, it is parallel. How do you know? They look like it, for one. But what if they looked a little different? We're going to go over to the one on next to it. Doesn't necessarily look like they might be in parallel. Some of them get a little bit more complicated. So if you highlight the whole node on both sides, or highlight all the nodes, and you see that the same color is on the top and the bottom of the elements. That's when they're in parallel. So parallel. ABC on this one. This is between A and B.
Parallel.
Okay. So again, if I highlight this, on the left they're all blue, on the right they're all red. Goodness. Okay, A to B here. Parallel. Probably seeing a theme here, but okay. What about this one? Also parallel. Okay. Okay. All right, so this one is a little bit more complicated. So some of it may be parallel, some may be series, and you're going to need to identify. So take a minute and try to calculate our equivalent here. Okay. Once you're done with that, you can put your answer in. Oh, whoops, that's not the right one. I'm trying a new. All right, I'm trying a new thing, so hopefully you can put in like decimal points and other things in here now. Okay. So I think you can put your answer in once you've gotten it. Okay, one more minute. Definitely consensus. Good job. So trick here is to notice something about this circuit though. What do you see? What's going on with the 8 ohms, and 16 ohms? It's shorted. So you have to notice that that's a short. So because you have a wire and across the 16, remember it's the same voltage across each one, then you're going to basically ignore it. So I can either cross this out, and then from there noticing that the top and the bottom of, or the whatever, left and right, the coloring on one side of the element is the same blue as the coloring on the right side, which is red, or bottom side, whichever one. So because there's two, you only have two elements, they would be 4 in parallel with 4, so I would write it as 4. The two little symbols mean that's a parallel form. So parallel is going to be 1 over 4 plus 1 over 4. Get a common denominator there, and it's 1 over 2 over 4. And then you can flip the 4 over 2 to give you 2 ohms. Okay. So as I was walking around, that's one thing I noticed is that some of you are not seeing that that's this, like you can ignore the 16 and the 8 and the 8. So if that was the case for you, does that make more sense now of why you need to ignore the 16 and the 8 and the 8? Okay. Side note, like 8 and 8 would be a series connection, right? So you can see that, yes.
If there was no short, would it be could it be the 8 and 8 be a 16, and then could it be parallel with the other 16?
Mm-hmm. And then if you did that, then it would be in series with the 4. So it'd be 16 plus 4 in parallel with the other 4. Yes, if that was the case and there was no wire there. Okay. Okay, so make sure you understand series connections, parallel connections, being able to combine them to reduce them down into what we call this equivalent resistance. So this technique can be used in a more complicated circuit, which we're going to get to, especially current dividers. You want to reduce it down to where you only have 2 resistive kind of branches in order to fit it into kind of the form of a current divider. So what happens when we have, say I put a battery, oh, I'm really horrible at drawing. Okay. Should go find a picture of a battery. Okay, here's my battery. I have the little node on the top and the thing on the bottom. So, plus minus. I should draw this upside down. I don't like my plus on the bottom. Okay, so I'm going to put my battery. Okay, ignore my title on here. It says 2 resistors impact circuit. Okay, just crossing that out. Okay, so say I have a battery and I have different resistors. I'll call them R1, R2, R3. These are known values. And I have my battery, which is going to be rated at whatever battery, 1.5 volt, 3 volt, 9 volt, whatever size battery I have. So let's just say I'm using a 1.5 volt battery. What happens with the current in this circuit? Notice that there's only one branch, so I'm only have one current that goes through it. So the current through the R1 is the same as the current through R2, it's the same as the current through R3. I'm just going to call this all I. What does this mean when I have the arrow right next to a wire? What's going on here? It's what? It's not going to change the voltage. What changes voltage? What changes voltage? That was a hint. You have to have a resistance to have a change in voltage. So it doesn't change the voltage. It's going to just have the current flowing through it. So anytime I have a wire and I have an arrow next to it, it's just meaning the current flowing through that wire. I've drawn the arrows that they look like they're going through the resistors, but that's the meaning the same. All of this current is flowing every single place within this circuit. As long as I don't hit an extraordinary node, that's going to be the same current flowing everywhere through there. Does that make sense? Okay, so I'm going to reduce some of the arrows here. I just wanted to point that out. Across every resistor now, there's going to be a change in voltage. So I could draw the arrow, I like this, or I could draw it right before, and it's going to mean the same thing. It's the current. I can draw it like this. All of that means the same thing. It's the current going through that branch. It just is meaning current in that branch. So if I wanted to label this, I could label the voltage now. I'm going to call that V1. So there's can be a voltage drop now across any resistor that I know current is flowing through. I'm going to just kind of remove these just so that it's easier to draw this. Okay, so then I know that there's voltage across this one and voltage across this one. So One current because I don't have any extraordinary nodes. They're all ordinary node connections in there. One current, so I can't do a current summation. What can I do here to get an equation? Not a current divider. I'll describe the current voltage divider in a second, but how do I solve this? If I wanted to find the current and the voltage here, is there a way to do that? KVL, KCL. So not able to do KCL because we don't have any extraordinary nodes. So KVL would give me what? Okay, so I'm going to get all the summation of all these voltages, right? So when you see a circuit, it's not going to always be labeled the current in there. It's not always going to be labeled the voltage across things. So you can always say, well, there's an unknown. I'm going to create a variable for that unknown. So you can go in and arbitrarily say, like, I'm going to guess the voltage is this way or that way. And it doesn't matter which way you put it. If you have a voltage like a battery there, you know that the positive is probably going to be most likely nearest the next positive to it. So that's where I made an educated guess of like, I'm going to keep it this way. But you could actually label it, solve the circuit, and then be like, oh, I got a negative voltage for that. It must mean it's the opposite way, but I'm going to leave it as is because that's how I solved my circuit. Does that make sense? So once you've labeled it arbitrarily, don't change it, even if you get a negative sign. Just put your answer in the negative. Okay? All right, so our voltage loop, I'm going to do a plus, a minus, minus, minus. So my equation will be plus 1.5 volts, minus V1, minus V2, minus V3 equals 0. So now I know one more equation. V equals IR. So I can determine for each of these, V1 is going to equal what? What is the current there? What variable did I call it? I. And I am going to put R as a known, so I'm going to just color it a different color, because R I'm going to treat as a known value here. What is V2? Sorry, I didn't label R1. IR2, correct. And we have an equation for V3. I saw you mouth it, so IR3. IR3. So there's a theme here. So now I have 4 equations and I have 4 unknowns. So remember, when you're solving a system of equations, you need to have as many equations as you have unknown variables. So in this case, 4 variables, so 4 equations. Here's all our 4 equations. How do I solve this? Do what?
Plug it in and solve for I.
Okay, we can plug it in. I think it's in Math 2250. You can do a matrix if you want. You can solve it with a matrix form. Whatever way, this one's more simple because all 3 of the V1, V2, V3 has just one unknown I in there. So if you plug that into the original equation, you have one unknown, one equation, and it's easy to solve. But a lot of times these will be like more complicated circuits, so you could put it into matrix form and actually go use a calculator online to do matrix solution. We'll go over that later when we get into a little bit more complicated circuits. But this one is simple enough. We can just say, okay, I'm going to substitute in. So I'm going to substitute these into 1, and I'm going to have 1.5 minus IR1 minus IR2, and then minus IR3. And with that unknown, one unknown in one equation, I can solve that I is going to be equal to 1.5, and then I just a summation of all these. So one thing I notice here is that V is equal to I over R. or I times R. And my R are all of these are in series together, so I could actually have just noticed that they were in series and kind of redrawn the circuit with one equivalent resistance. Not V1, 1.5. And having the voltage across it would be I is equal to 1.5 over R equivalent, where the R equivalent is the summation of all those three. So either way, two different ways to look at it: simplify the circuit first, then solve for I, or write KVL, KCL, use Ohm's law for any other unknowns, or to get more equations if you need it, and then manipulate the equations to get one unknown with one solution. So now we know I, we can go back and find the voltages across each one. So now I can just go back and plug in I to these equations and get V1, V2, and V3. So purple. V1 is this value of I, R1 plus R2 plus R3 times R1. V2 is the same times R2 and V3. So what I notice here is there's some similarity between each of these. The voltage is 1.5 volts, and each of these values has to add up total to the 1.5, right? That's basically what this equation is saying. The 1.5 is equal to the summation of all of these. So each of these is just a fraction of the 1.5. And now we have a way to describe that mathematically as the voltage across V1 is going to be the total current and the voltage with a ratio based on R1 value, right? Because R1 over kind of a summation of all of them. So it's basically the percentage that R1 is of the total. Same thing with R2, or V2 is going to be R2 over the total, so it's basically a ratio of those resistances based on the value of R2. V3 is the same, it's the ratio of R3 to the total times my total voltage that's there. So if I can look at a circuit and say, well, I know between one branch, the voltage on the top and the voltage on the bottom, I can use the same voltage divider idea. So if I know the voltages between the top and the bottom of a series of resistances, then it's just going to be a fraction of each of the overall voltage based on the resistance that I'm looking across. Okay, so this is what the voltage divider is it's just saying that this configuration, which is a voltage in one branch, that's one key, it has to be one branch, and then I'm dividing up the portion of the voltage amongst them. That's all it is a voltage divider. Okay? So what you notice about the equation is that the voltage I'm trying to find across a specific resistor is going to be the total voltage, meaning across all resistances, and then it's the portion it's going to be the portion of the resistance I'm looking across over the total of all the resistances in the branch. So if you don't remember this voltage divider equation, you now know the technique on how to actually find this equation. Okay, so if you've forgotten it, you can still derive it, and using KVL and Ohm's law. Okay, all right. Okay, so example, go ahead and find the voltage across R3 in this example. And then once you get that, go ahead and put in, I'm going to figure out how to erase this. Just deleting that one. Okay, and then just put in your answer. Oh, it doesn't show the top. Okay, it's the same link as you had before, but I'll put it up again. I like the significant digits that you guys are going to. You're gonna love that. I love to be like, it's 2.8. It is, so as you guys are still figuring this out, what you do in situations like this is you're gonna use your hand calculations to get an idea of what is the current, what is the voltages, what am I trying to design it for, try a design, and then you use a simulator to go and make sure you're accurate. So using 2.8 is easier in calculations than 2.809. So I'm fine with you guys rounding up or rounding down a little bit. So you're gonna see also in the homeworks and the quizzes, there's usually a percentage that you can get on. And that's because of the rounding errors you'll see. And again, it's, love it. There you go. So great job. Looks like everybody again came to a consensus, so you guys are doing well. Okay, so I am going to find VR3 is the total, which is 6 in this case, times the resistance I'm looking at, and I want to make sure to use K as 10 to the third, and then I sum all of these, so 1.5K plus 1K plus 2.2K, and that gives 2.809, whatever it was. So 2.8. All right, questions on this? All right, that's the voltage divider. So current divider does what it also says, is that you're gonna have current coming in, and then it's gonna split and go through different branches. Again, the way it splits depends on the resistance in those branches, and that's what's gonna determine the amount that goes. So if I have, no, let me draw it first. Okay, so with current division, remember current is the same in a branch, so I have to have an extraordinary node. So say I have 1 amp. And again, these are known values. So I'm going to call it R1 and R2, as that does not even look different. Okay, I'm going to do them in red. Okay, these are known values. So my 1 amp comes into my extraordinary node up here. and then it splits into R1 and R2. So my current in these branches are going to be different, right? Because it can only be the same current in one branch. So because nothing is labeled, if I was to just be given this circuit, I'm going to say, okay, I want to label my voltages and currents that I don't know in here. So in this branch, I'm just going to call it some purple. I'm going to call it some current. So I'm going to say I1. And I'm going to call this one I2. I also know that across this, there's going to be some voltages. So I'm going to call this V1 and this V2. What is the current here? Say it louder.
1 amp.
It is 1 amp, right? So even though it's a bend in the wire, this is one thing you got to get used to, that as mechanical engineers, you might not see this right away. And even our beginning electrical and computer engineers, seeing the bend in the wire is hard because it usually think about physical things. But this is a little bit more abstract, where this wire is the same. Like I could say, like, this wire goes around and around and around and comes back here. All through this current is going to be the same. Okay? So that is a hard concept that takes a minute. So just remember, in the branch, it's all the same current. And you're going to hear me repeat it again and again. So that is the same current. It's 1 amp. What do I notice about V1 and V2? They are in parallel. And the node on the top is the same as the node on the bottom. So because they're in parallel, parallel means that my voltages are the same across that. So the voltage is the same, currents are different. For series, your current is the same and the voltage is different throughout the branch. I might write that because that's a good thing to remember. Okay. So series, so these are kind of a side note. Series connection, you have voltage can be different. Current is the same. Parallel, voltage is the same. Current is different. Okay? So a little side note, make sure you understand that concept. Okay, so back to this one. Okay, so we have one equation, V1 is equal to V2. What else can we do here? Oh, another note. There is always voltage and unknown voltage across a current source. So since V1 is equal to V2, I'm just going to call this Vx. That's also equal to Vx. So that is some unknown voltage there. So we can't do a voltage loop through Vx because that's, well, that will just add another unknown. So we typically try to avoid a voltage loop through a current source. Okay, so if I'm avoiding that loop with the current source in it, do I have another loop I can take? What other option do I have for a loop?
Through the resistors.
Correct. So I can do a loop through the resistors, and that gives me the same as what I have, right? Plus V1 minus V2 equals 0. So if I didn't see that that was like, oh, in parallel, and so I don't see it, I can still do voltage loops and see, get the equation for that. All right. Okay, current summation. So what will that current summation be? Say I do it on the top node.
One half minus I1 minus I2 equals 0.
Correct. What if I do it on the bottom?
Flip the signs.
It's just going to flip the signs. So I have one going out, and then I1 and I2 coming in. So yeah. And that's the thing about parallel, is that they're going to be the same on both sides, but they're going to be a sign opposite. So, all right. So now I also know Ohm's law. So I have an equation with V1 and V2, and then an equation with I's in it. So I need to convert one or the other. So I also know that V1 is equal to something. What is V1 equal to? I1, R1. R1 is known. I'm going to put it in this. And V2 is? I2, R2. So I can either solve for R1 and then put the equation in for V1, or I can just do V1 is equal to V2, whichever one I feel like. I'm going to do the equals. So I'm going to do I1, R1 is equal to I2, R2. And then I can solve this for one or the other. So now I can solve this and then use one of the current summations and say 1 minus this I2, R2 over R1 minus I2 equals 0. And now I have an equation with one unknown. So from here I can solve this for I2. So for I2 I'm going to need to combine these. So I can do R2 plus R1. Let me back up. Okay, R2 over R1 plus 1, which can be written as R1 over R1, is equal to 1. And so I2 is equal to, combining this, I get R2 plus R1 over R1. So this is 1 times R1 over R1 plus R2. So I can do the same thing and get an equation for I1, and I1 is going to be I times R2 over R1 plus R2. So now I see, like, okay, again, this is the current that's my supply, and it's a ratio of the R2, which is the branch opposite, is going to determine how much flows through this branch. So R2, which is in for I1, R2 is in the opposite branch from it, or not the same branch. So it's going to be the ratio, instead of the same resistor, like with voltage, the other branch's resistance is going to determine how much it's going to go through. Okay? So in this case, it's going to be I times the other branch's resistance over the total resistances in the branches. Again, if you can't remember these equations, you can go through these steps to derive it. So, current divider equation. Oh, I don't like this one. Okay. I copied this from somebody else. I don't like this one. Okay, so this is going to be I of whatever branch you want. So IN times I total, so this is all the current summation, times opposite branch resistance, all over the summation of both branches. So if you want to reduce the circuit down, you can reduce the circuit now to be able to reduce it to this form. This form only had 2 branches and a current coming into it. So you would have to reduce it down to these 2 branches with an incoming current or outgoing current. So if my current was going down instead of up, and my currents were still labeled as down, you can see that the current flow should come in and then go through. So if you think of this as water, water is going to come out and then go down. But if my water is forced through pressure to go the opposite way, and I label my currents going the opposite way, then I'm going to have a negative current there. So I could use the same equation and just do negative of that. So let me draw that. You looked very confused when I said that. So let me draw what I'm talking about. Okay. I1, I2. So say I had 2 amps going in this direction and the current's labeled in this direction. Hopefully you can visually see that they're going to be opposite. So in this case, I1 will be -2 times 2, the opposite branch resistance, R2, over the summation of both. So it's going to give you that negative in front of it. Okay? So just like Ohm's law, if you have opposite, you're going to get a negative. Otherwise, it's positive. Okay. So again, these only work for 2 branches. So we have to reduce the circuit down to 2 branches, and then we can use the current divider equation. Otherwise, we can go through all the steps we did with KCL, KVL, and Ohm's law to be able to get the equation set. Okay. You're welcome to use this equation. All this equation is doing instead of, so these are called conductances instead. And it's 1 over the same branch resistance. So if this one looks better to you, feel free to use this one. So you can use the same branch for both, but you would have to take 1 over that Rn and then 1 over each of the branches resistances. So this also works for parallel branches up to more than just the 2. So if you like this, you can use this. Okay, so let's look at this. This is not your homework, so I'm going to cross that one out. All right, so in this case, we have, okay, this looks a little confusing. This resistance is the 0.68 kilo ohm. This resistance is 0.82 kilo ohm. This one is easy to see, R4, and then R1 is the 1.1, which is this resistance. And then 35 milliamps is the current that's going up into those. So what would you need to do here to get one resistance in this middle branch? So R2 or R1 plus what's
1 over R2.
Yeah, correct. So you have to put R2 and R3 in parallel to each other, and then it's in series with R1. So that would be, then you have to treat this as kind of your new resistance in that branch. Okay, so take a minute to find IR1 through resistor R1. Okay, next time I will have these already on the slide to make this easier. So again, find IR1.
I guess I just don't really know. Are we supposed to do this as the first step?
Nobody else wants to put any answers in. Ah, there we go. Now it's. Six, 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 4, 5. Okay, I had a feeling we were going to have a little bit of more variety on this one because of the rounding possibilities. So interesting. Okay, so one, like half of a minute, 30 more seconds. All right, so we had more variety this time. So as I go through, the answer is like 17 point, rounded up to 0.7. So it is 17.7. So if you didn't get that answer, as I go through the solution, ask questions if it's different than what you did, just so that you make sure you are understanding where you might not have seen it correctly. So combining these, we're going to combine these two first. So 1 over 0.68k, or you can write it as 680, plus 1 over 820. You can either get a common denominator and then put it into your calculator, or you can just put that itself into the calculator. If you get a common denominator, it's going to be 820 times 680 over the summation of those. And that ended up being, I had 371.73. And then you add that to the R1, so the R1 is going to be in series with that one. So the R equivalent in this branch will be 1,100 plus 371.73. And so this total branch, one more page. I can redraw this. And I'm going to have the two branches. Now this looks a little different than what you've seen as far as the one wire. This is the ground element, and the ground element, you can see it drawn like this. You also might see it drawn like this. Sometimes you'll even see a little dot. All of that just means a ground, and that means 0 volts is at this ground. I can draw a wire between all of my grounds, and that's gonna look more similar to what you've seen. So if for now it looks better to you, go ahead and draw a wire to all of your grounds. So now it should look kind of like what you've seen in the other ones. This was 35 milli. And this is 1,371. And this was 1,100, I think, or 500. Okay. All right, so with this, I'm trying to find the current in this branch. So I1 in this case, or R1, I guess is what it was called, is the current in this branch. So the current going through here is going to come in and split again, but the summation of those is going to be what goes through R1, and so that's the whole current in all the branch. So I can just have to find that, and that's going to be 35 milli times the opposite branch, which is 1,500, over the summation of both of these branches. Okay, I miswrote that. 1. I'm missing a 1 in there. 371.73. And that ended up being, what was it, 17.7 milliamps. So make sure you're using the right units too, and that you don't forget to use K, and you don't forget to put in milli, because very different numbers if you're not using those, the milli and the K in there. All right, any questions about this one? I think this had more variety on answers, so. Okay. All right, now the next topic we're going to talk about is jumping to sensors. So sensors are going to be a device that's going to measure something from the environment, or it can be something that I change so that the signal will change. So you can have all of these different sensor types. This is one example, is a photoresistor. The symbol for the photoresistor in a schematic will look like this, where you'll have a wire or a little arrow going through it. That means that it's variable. So this is a variable resistor, and light means the little arrows next to it. You may also see this is also a common one where you may see little arrows going off of it this way. Those all just mean it is a photoresistor. So photoresistor, it measures the light, and its resistance changes based on the intensity of the light. So it's kind of a cool little sensor. As shown here, like there's lots of different type of sensors. The potentiometer is another really common one we use a lot. And it also has that little arrow going through it, or just in the middle. It will look, either of these symbols are still potentiometers. So you may see it also go through. So those two would also mean just a potentiometer. When you see a little arrow next to it, that is either it's photoresistor or it's emitting light. So the little arrows outside of the element mean it's either absorbing or emitting light from it. Okay, so a lot of different ways that we can measure. And I thought this was a really neat video. So this video that I'm going to show, okay, if I can get off.
need to put a backup battery in your home. So most people don't know this, but almost 100% of homeowners that make the switch to solar this year through ES Solar will do it for $0 down while getting paid thousands of dollars up front by Rocky Mountain Power to put a backup over the life of the system.
It didn't let me skip it. I'm like, I already watched that. Sorry.
Building a RAG application is so easy, and I'm going to show you how to do it using AstraDB, LangChain, and JavaScript with just under 50 lines of code. But firstly, what is AstraDB? AstraDB is the
Sponsored by PCBWay. This is a potentiometer. It's an adjustable resistor. They come in many shapes and sizes. We can insert them into test boards, connect wires to
Sorry, I'd
them,
watched
solder
things on
directly to them.
Okay. All right, I don't know what happened to the display. And we won't watch this. It like totally died. Okay. Okay, I don't know what that was about, but.
Or solder them onto circuit boards. They usually have a dial, a slider, or an adjustable screw head, which lets us change the resistance of the component. They are represented with symbols like these in engineering drawings. We can use them to manually adjust the voltage or current in a circuit. When used to adjust current, we call them a rheostat. I'll explain how to use both of these later on in the video. See this game controller? Well, the joystick has two potentiometers. One measures the up and down movements, and the other measures the left and right movements. This is a servo motor. We use them in robotics. Inside, we find a small potentiometer, which is used to check and control the position of the arm. This radio uses a potentiometer to control the volume. This DC power supply uses a potentiometer to control the supply voltage. This audio equipment uses a slide potentiometer. So where have you seen them used? Let me know in the comment section down below. Okay.
So kind of cool. If you want to learn more about potentiometers, how they're physically made as mechanical engineers, that might be interesting to you. I put this link to this video on the Canvas course under the Lecture 3 material. So feel free to go watch that if you have interest in it. Again, homework will be due on Thursday. It's going to be voltage and current dividers, so that will be this week's homework. All right, see you guys on Thursday.
Okay.